Welcome to CS270. Today we're going to take a look at networking. Um, so most of the time, most network applications are based on what's called a client-server model. So you have a server running on some computer out there. This might be a server running on your home computer, but more likely it's something in a data center somewhere. um, the server manages some kind of resource and provides a service for clients. So the clients are the individual users who connect to the server. So typically there will be one server and many clients who are using it. If you think of a website, for example, um, there would be a server running the website, and each client, each user of that website connects to it. So you have one server, many clients. In the case of a web server, the resource that it provides would be the web pages that are there, or maybe some kind of service. For example, the Amazon website, the service that it provides is the ability to buy things and have it shipped to you. The Netflix site, the service that it provides is streaming video, and so on. So, for the most part, these days, that kind of networking is done over the internet. And you'll notice here it mentions the global IP internet with an uppercase I, and there's also the word internet with a lowercase I. Well, an internet with a lowercase I is just a network that's made up of many individual networks connected together. And the most famous of these and the largest of these is the internet with an uppercase I, which uses a protocol called IP. Well, actually, a family of protocols. So there's IP. This is the internet protocol. It's the uh, lower level protocol that provides a way for packets, pieces of data, to be sent from one computer to another. So it provides what's called host-to-host communication. When you send a raw IP packet, you don't specify which process on the server you want to connect to. You just provide the address, the name of that server. On top of IP, there are a couple more protocols that give us functionality to make this much more useful. UDP, the Unreliable Datagram Protocol, is based on top of IP, but gives you a way to connect process to process. That way, a single computer can be running many different servers. And when you connect, you specify what's called a port that tells the server which of those processes you want to talk to. So, for example, a server running out there might have one port that's used for the web, another port that's used for sending and receiving email, and so on. Now, UDP, like IP, is unreliable. That means if you send a packet, send a bunch of data to the server, there's no guarantee that it will get there. And if you send several packets, there's no guarantee they will get there in the same order. This is useful for some things. Many games, for example, are based around UDP. Um, but for things like a web server or so on, it would be pretty bad if the response that the web server was sending back was sometimes missing pieces because those packets didn't get delivered. So there's another protocol called TCP, the Transmission Control Protocol, that gives us a way to make connections from one machine to another. Again, like UDP, process to process. So we're communicating with an individual process running on the server. And those streams are what's called reliable, meaning if we send something, we know that either it will get there or we'll get a message back saying we've been disconnected. And also, it's a stream of bytes rather than of packets. So if I send a sequence of 20,000 characters, then that might be divided up into packets and then reassembled when it gets to the server. But from the client process and server process's point of view, it's a stream of bytes, just like a file. In fact, when we get to network programming in some of the later videos, we'll see that it actually is implemented as files, following the Unix philosophy that everything is a file. So to access these things, we need a programming interface, which we'll talk about in a later video, but that is called the sockets interface. So a socket is one end of a connection or one end of a communication in the case of something like UDP. So TCP tends to be the most commonly used of these protocols. Well, of course, IP is really the most commonly used because UDP and TCP are both built on top of IP. But between UDP and TCP, TCP is more common because that reliability and knowing that your packets will arrive in the same order and being able to think of things as just a sequence of bytes without having to worry about how they're divided up into packets is very useful. However, the processes that TCP uses or the procedures that TCP uses to ensure that things are reliability do introduce a cost. It can take a little longer to receive a packet because you have to wait to make sure that all the previous packets have come in. Everything has to be acknowledged from the server back to the client to say, yes, I did receive this packet. So UDP is still used for many things. In particular, computer games very often use UDP. It's if you're playing a first-person shooter, for example, it's much better to lose a packet and lose one command that you sent rather than pausing the connection for potentially a long time, hundreds of milliseconds or even thousands of milliseconds, to wait for those to come in the right order. UDP is used for a few other things as well, but by and large, when you see a program using it these days, there's a good chance that it's a game or something similar that requires a very low latency protocol, but can survive this unreliability. So in an internet application, that is the combination of both the client and the server, it's organized a little bit like this picture indicates. So we'll look at the client side, but the server side is really the same thing. The client, the program that's running itself, for example, your web browser, is user code. That is not the kernel. It's a program that is running on the computer, and we'll see in later lectures how to write programs like that. It has to communicate with the kernel. It can't access the network hardware directly. It's the operating system's responsibility to do that. So it communicates with the operating system through the sockets interface, which is a collection of system calls to make connections and destroy connections and bind connections to particular addresses and so on. So the kernel has an implementation of what's called the TCP/IP stack. This is the code that decides how to format those packets, put them together, and so on. But those also have to be then communicated to the hardware. So the kernel code dealing with TCP/IP will also talk to the network adapter through whatever its hardware interface is. That might involve interrupts. It probably also involves things like direct memory access for the hardware to be able to put the packets into somewhere in memory where the kernel can find it and pass that data back to the client. And then the network adapter, it will talk to whatever network it's plugged into. If you think about your home network, this network adapter might be a wireless adapter, which is then communicating with your wireless access point, which is plugged into or maybe a part of your cable modem, for example. That cable modem then transfers those packets over the global IP internet through your internet service provider, then through the other internet service providers that they're partnered with, until eventually it reaches the network adapter of the server. That network adapter of the server then communicates with the kernel in the server to deliver those packets, and the kernel of the server communicates with the server process, which receives those packets or that byte stream in the case of TCP/IP, and decides how to handle them. And all of these connections are bidirectional. It's not just that the client sends things and the server receives them, but the server will send a response, and that will go in exactly the same way as the client's messages through the server's kernel, its network adapter, through the internet, to the network adapter of the client, to the kernel of the client, and then to the user space code of the client. So from a programmer's point of view, hosts on the internet are named with 32-bit IP addresses. So something like this. Each computer on the internet, subject to some special cases, has an IP address. Then somewhere, we'll talk about this in the next video, those IP addresses are mapped to particular names, domain names. So an IP address will look something like this, a sequence of numbers. I said they were 32-bit. Well, each of these numbers is going to be a 8-bit number, so 0 to 255, and there will be 4 of them. The DNS, or the domain system, allows us to have more user-readable names. Rather than just numbers, and rather than only having 4 of them, we can have names as text and a sequence of any number of those. So www.cs.uky.edu, or my virtual machine, nmore0.cs.uky.edu. And by making a connection using TCP, a process running on one of these hosts, one of these computers, can communicate with a process on another host. So I said IP addresses are 32 bits. That isn't entirely true. That is true of what's called IPv4, the Internet Protocol version 4, which has been around for a really long time, since the early to mid 80s or so. There were other versions of the Internet Protocol before that. The problem is, with 32-bit addresses, 2 to the 32 is about 4 billion. So that gives you a maximum of 4 billion hosts, 4 billion computers or devices on the internet. Well, that was fine in the 80s, that was fine in the 90s, but these days it's not so fine. There are more than 4 billion computers out there, particularly if you count things like smartphones. Also, we can't actually use all of those addresses. Some of them are reserved for special use. They're also divided up according to the owner of those addresses, so that it's not possible, or not usually possible, to have one address belong to one company and the immediately adjacent address, add 1 to it, to belong to another company. Instead, you would tend to get your addresses in blocks, which means there could be some wastage if you're not using as many computers as are in your block. So because of those issues and other ones, the Internet Engineering Task Force in 1996 developed a protocol called IPv6, Internet Protocol version 6. In IPv6, we have 128-bit addresses, so 4 billion times 4 billion times 4 billion times 4 billion theoretical potential hosts, which is, I think, well more than we'll ever need. That would be enough to give one address to every grain of sand and still have many, 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 many left over. IPv6 hasn't had as much take-up as the IETF would have liked. As of about 20 years after its introduction, only about 4% of network communications used IPv6. These days, the number's a little bit higher, but still not necessarily a lot higher. Chances are the computer that you're using at home, the network connection that you have, is probably IPv4 only. So in this chapter of the book, I'm going to focus on IPv4, but everything I show you about how to do network programming, how to write code that communicates with the server, we'll see how to do that in a protocol-independent way. So your code will just work with an IPv6 client and server if that's what you have. So a little bit more about those IP addresses. So they're 32 bits. They're stored in a struct when you're programming called struct in_adder, internet address. And they'll be stored as a uint32t, so an unsigned integer of 32 bits. This is maybe on our system a type def for unsigned int. On other systems, maybe it's unsigned long. The particular type isn't important as long as we use this type def. One kind of strange thing, not necessarily that strange historically, but strange when we think about most of the computers connected to the internet, is that IP addresses are stored and transferred in network byte order, which is big endian. Well, the x86-64, as well as most as the ARM processors on most cell phones, for example, use little endian byte order, which means we do have to do some conversion when we're translating IP addresses into a form that we can use to communicate over the network. So we'll see a couple of functions to do that later. In general, everything in the IP protocol and the TCP protocol, in fact, uses big endian byte order. So the port number, which we'll talk about later. That means we have to do a little bit of conversion. So we have these functions. H2NL, that's host to network long. This is long, what long was in the 80s and 90s, so 32-bit, into HL, network to host long, 32-bit. H2NS, host to network short for 16-bit values, and into HS, network to host short, to convert a 16-bit value. Now, it turns out converting between big endian and little endian is a self-inverse operation. That is, H2NL and into HL actually do the same thing, but there are two different functions, so that machines with strange byte orders can still use those functions. They'll just be implemented differently on those machines. Why was big endian chosen? Well, at the time that IPv4 was being created or was being designed, big endian machines were probably were definitely more common than they are today, and were probably more common than little endian machines at the time. We have to pick some byte order, so this is the one that they chose. So those IP addresses are typically written in this dotted decimal notation, so something like this. And those correspond to a 32-bit number that we can then put into the sadder member of the struct in_adder. So for example, 128.2.194.242 would be 0x80 for the 128, 02 for the 2, C2 for the 194, and F2 for the 242. Now, in order to convert something like this, which might be provided to you as a string, for example, into something like this, you could do some parsing yourself. You could use something like scanf, for example. But there are some functions that will do that conversion for you. We'll talk about those when we get into network programming. Get adder info, get name info, to convert from a numerical address into a string representation of that address for get adder info, and get name info to do the reverse. Get adder info and get name info also give you access to those domain names. So the IPv4 address space is divided up into different network classes. The class of a network says how much of the 32-bit address is used for identifying the network and how much is for identifying the host within the network. Remember, the internet consists of a bunch of smaller networks connected together. So a Class A network has 8 bits to identify the network, and the first of those bits is always 0. That's how we identify that it is Class A, and 24 bits to identify the host within that network. So there can only be 256, actually 128 because of that 0, such networks. So not a lot of them out there, but each one can have about 16 million hosts on it. Class B networks are a little bit bigger. They have 16 bits of network, of which the first 2 bits are always going to be 1 and 0, and then 16 bits for the host ID. So that allows us to have about, well, 16 bits would be 64,000 or 65,536, but we've lost 2 of these bits to encoding the class, so that leaves us with 14 bits, or about 16,384 different Class B networks, and each of those can have around 64,000 hosts on it. Class C network has a network ID that's 24 bits. The first 3 bits are fixed, so really 21 bits, which gives us about 2 million different networks we can have in Class C. And the host ID is 8 bits, so we can have around 256 hosts. Actually, a few less because some of those addresses are reserved. So we could have a lot of Class C networks, but they can't be very big. Fewer Class B networks, they can be bigger, and very few Class A networks, but they can be huge. So something like UK has a Class B network. UK's IP addresses look like 128.163.something.something. So 128.163, half of the address, that's 16 bits. And you can verify that the first 2 bits of 128, the higher order bits of 128, are 1 and 0. In fact, 128 is 1 followed by 7 zeros in binary. 163 then would be the next set of 8 bytes. And then the remainder of the address identifies a particular computer or particular host within UK's network. So we often write out the network ID in a form like this. We write the IP address, but we fill in 0 bits for the host ID. In this case, the host ID starts at bit number 16, so we'll have .0.0, and then we put a slash after the address and indicate the number of bits that belong to the host, or belong to the network ID, rather. So 128.163.0.0 says I'm talking about a network where the network part's the first 16 bits, 128.163, and the host part would come after that, and we write zeros when we're writing the network ID. So that's Class B. There are also a few networks that are reserved for private use. Those are 10.0.0.0/8. So if the network ID is 10, so that would be 0.0.0.0.1010 in binary, then that is a private address. And you can have up to 64 or up to 24 bits, about 16 million hosts on that network. 127.16.0.0 is it's actually a collection of several Class B networks. 192.168.0.0/16 looks like a Class B, but if you look at the bit pattern, it turns out it's actually a collection of 256 Class C networks. If you see an IP address that looks like this, that starts with a 10, or starts with a 172.16, or starts with a 192.168, then you know you're talking about a private network. Um, for example, if you were on campus and able to connect to UK's Wi-Fi, you would receive an IP address that looks like this. Your IP address can't communicate directly with the outside world. These private IP addresses aren't routed over the global internet. Every company that runs its own wireless network will use these addresses as they see fit. And somewhere between you and the server on a router, for example, that UK provides, you'll have a computer or other hardware that will do translation of these addresses into public addresses. And the reason we do that is because of those limited number of IPv4 addresses. Only fewer than 4 billion addresses are available, but by using these internal networks, we can have many more computers on our network than the number of publicly available or publicly accessible addresses. That does require some work on the part of the routers to, when a response comes in, for example, to figure out which of those internal addresses it was really meant for and pass it along. And when you are on one of those internal addresses and access the server, to map from your internal address to an external address, and there will be fewer of those than the number of internal addresses, sent to the server, and so on. All right, that's all I wanted to say about TCP/IP for the moment. In the next video, we'll see a little bit about the domain name system. So thanks a lot.